solving MPI integration problems with Spack. And we have Greg Becker from Lawrence Livermore National Lab. So he's a computer scientist there. His focus is on bridging the gap between research and production software at LLNL. His work in software productization has led him to work on Spack, a package manager for HPC, as well as scalable I/O formats for performance tool. He's been at LLNL since 2015. He received his BA in computer science and maths from Williams College in 2015. Welcome, Greg.
Thank you. So I'm going to talk about Spack today, and specifically how we solve problems related to integrating MPI into HPC codes. I'm going to start by talking a little bit about what Spack is for those of you who aren't familiar. Then I'm going to talk a bit about what we do now to support MPI specifically. And then I'm going to move to talking a bit about current and near-term future R&D that we have going on about how we can better support things like MPI that users want to swap in and out. So modern scientific software is getting incredibly complicated. This is MFEM. That's a dependency graph, 31 packages, 69 edges. MFEM's actually kind of small. That's LBAN, 71 packages. And things get even worse from there. That's our ConDop. It's a genome data analysis tool. The bioinformatics world is definitely full of some of these scary-looking dependency graphs. But we're talking about 179 packages, 527 edges. This is not the sort of thing you can manage manually. Or another way of saying this, for a particular code with 70 packages, 4 MPI versions, multiple platforms, multiple compilers we might care about, a couple different versions of each, you might well be talking about tens of thousands of possible configurations of your software. And how can we not only build that software, but know which of that software we're building and let users decide which one they want? So one of the important contributions of Spack is a syntax for describing points in the build space or regions in the build space. So if I want to build MPI leaks, this is an MPI debugging tool from Livermore, I can just say Spack install MPI leaks. And I can add arbitrary levels of detail of what I care about. So I can say I care about the version, I care about the compiler or the compiler version, build options, compiler flags, targets. It's a telescoping syntax, so I can say it about my dependencies. And it gives me the full ability to specify anything about the build. So that's one of our contributions. Another is the dependency resolver. This is how we fill in the details, right? If you say Spack install MPI leaks, you still need to install at some version, and you need your dependencies to be at some versions. So how does Spack figure that out? We have a concretizer. We turn your abstract description into a directed acyclic graph. We send it off to an ASP program that fills in all of the details. And then we store the provenance just to be safe. The third important contribution of Spack is a repository of recipes that encode all of our collective knowledge of how to build these things. It doesn't do me any good to say, I want to build cryptkey with OpenMP turned on if I don't know how to actually turn it on in the build system. So our package files are fully parameterized or templated. What I mean is that once you get a concrete spec here as part of your install, That is everything you need to know about how to build it, and you write one script for how to build based on that. We don't have separate configuration or separate packages, files for different configurations. Less important or lesser contributions of Spack that we need to talk about a little bit to understand what I'm going to talk about further, right? There's a build engine behind all of this. Once you get that, Spack's going to fork a process. It's going to set up your build environment. It's going to set you up to use the Spack compiler wrappers. And Spack's going to RPath everything. And the reason we RPath everything is we think that things should work the way you built them, especially in HPC where often the person building and the person running are not the same person. How is the user supposed to know what environment variables you had set when you built if you're relying on LD library path to get your dependencies? So we hash each configuration. That's how we let them all coexist on the system. And then the RPaths allow you to manage that, right? You don't want to have to put something like this in an environment variable, but you don't have to because we use RPath. Spack also has added capabilities to handle binary packages. So a traditional binary package manager, you write a package file for every configuration you could possibly care about or that you think someone else could possibly care about, or at least as many of those as you have the patience to write. And you build it somehow, and you build it for the lowest common denominator because you want everyone to be able to use it. And you have a software stack, it's installed in /user, and no one in HPC is ever going to use it because it's slow. So in Spack, we have parameterized recipes, like I said. We have a build farm that we run through our CI system, and we build architecture-specific binaries. And so you can have as many separate stacks as you need out of one system. The only limit is how much build farm time you're willing to put up for this. And then anything that you don't build, well, Spack is still a from source package manager originally. The user can seamlessly integrate your binary packages with their source builds through Spack. Now, to make those binaries work is a little complicated because we're not just installing to /user, we're installing to arbitrary paths in user space. I don't know where my user is going to install Spack, and so I'm going to have to relocate the package. And fundamentally, relocating the package means rewriting anywhere that the package prefix or any of its dependencies appear in the package. That's in symlinks, that's in text files, that's in RPaths. All of those are easy enough to do. And that's also in strings hard-coded in the binary. And that last one is really hard to do. And because of that, when you're building these binary packages, you actually want to install them to extra long locations so that there's space in the binary to cut them down to wherever the user is going to install them. There's no way to expand the binaries. We tried, we worked on it, we kept working on it until we proved that it was equivalent to the halting problem. So now let's talk about MPI specifically. So Spack handles MPI and other things that share some qualities with it as what we call a virtual package or a virtual dependency. And basically that's saying the thing that we all care about MPI, which is that it's an interface and we can swap in different implementations, and someone might have built their package, written their package thinking about using OpenMPI, but we're all here, we probably want to use Mvapich, and we can swap that in at build time. We also have versions on the implementation or on the interface itself that can restrict which implementations you can use. Now, to get that interoperability to work, we don't only have to have the packages, the source, the code written to an interface. We also need to make the package files within Spack interoperable in some ways. And so there's several things we have to set up to get MPI to play nicely with the rest of the Spack ecosystem. One thing is we need some sort of way to get the location of the compiler wrappers, because you're going to need to inject those compiler wrappers. Most build systems are going to need to read those compiler wrappers to be able to understand what to do with MPI. Then additionally, we're going to have to set some variables to tell the MPI compiler wrappers to use the Spack compiler wrappers. Because I mentioned earlier, we wrap the compilers, so we have to set mpich cc and friends to accomplish that. So in Spack, I showed you an example of a package file earlier. Here's the same package file, but it's for a virtual package. So I've highlighted, we say it's a virtual package. And there are things that you can share among all of the implementations or all of the providers of a virtual package. In this case, it's a test method, right? We have an MPI hello world.c and .f that we use to test. And that test applies to any implementation. So we code it on the virtual package, not on the individual providers. We can also configure Spack to build with external software, and this is particularly important for MPI because of the way it's tuned to the local system. So you write some YAML that tells Spack where to find your MPI. You get your concrete spec. Spack will just trim off all of the dependency data below the external because we can't figure out with any real reliability how it was built on the system. We'll come back to that later. And instead of the dependency information, we just tell you it's this one. And that information goes into the hash 2. So that's great. And that's sort of the state of the art in integrating MPI with the rest of the HPC ecosystem. But it doesn't cover everything that we would like. We have these binary packages, and the binary packages were built with someone else's MPI. And I can rebuild, right? I talked about all these great ways that we can swap out different MPI implementations at build time. But we want to swap them out at runtime as well. And we want to do that in a way that we actually preserve the provenance and know what we're running. So we need to be able to relocate the package to change where the dependencies point to a different MPI. And then something similar happens when you go to run in a container, because the container runtime is going to have one MPI and the system's going to have another, and we need to be taking advantage of the performance of the system MPI. So how can we do this in Spack? We need a model for this sort of redeployment, and we need a way to actually modify the packages on disk to achieve it. So I've color-coded based on where these things stand. We have a new deployment and metadata model in Spack. We'll talk about splicing and rewiring. Splicing is the model operation of taking a DAG of a dependency graph and swapping in different components to change that dependency relationship. And rewiring is how we refer to the process on disk of actually redeploying the software so that it matches the new model. And the nice thing about rewiring is we don't really need to talk about it because we already talked about it with the binary package relocation. It's the exact same thing, right? We're changing the paths of the dependencies. We're changing the R paths. We already know how to do all of that. So I'll talk a lot about splicing. Then we're going to need some guardrails on this. I can give you an API today, right? The model is done. I can give you an API today that you can splice some packages together. But unless you're an expert in those packages, how are you going to know which ones are a good idea and which ones aren't? And currently, the state of the art in the world for this is you don't. You just find someone who's an expert, and they make an educated guess, and you hope it works. So we want to give you some guardrails that actually tell you something about how to do that safely. And then the last thing is we need to make some changes to our solver so that our solver can say, oh, you asked for these two, you asked for HDF5 built with this version of MVAPIC. I don't actually need to build anything. I can just cobble that together from existing binaries, and I know from the ABI information that that's safe to do so. So let's talk about splicing a bit. So for all of our splicing examples, we're going to use this hypothetical version of Trilinos that instead of being a heinous ball of dependencies, just uses MVAPIC and zlib. And we have a binary for Trilinos built somewhere out in Spack CI. And that's great because Trilinos takes forever to build. But we have a really high-performing system MVAPIC. We'll call that MVAPIC prime. And it depends on zlib prime. And Trilinos was built with MVAPIC and zlib. So the splice that we want to do is we want to redeploy Trilinos built against MVAPIC prime, move all of the RPaths over, all of that rewiring stuff that we can ignore. But we also want to preserve the provenance. So this black arrow is denoting what we call the build spec. It's just a metadata recording of how this thing was built originally. Now, in this example, Trilinos also uses a new zlib prime, that came in with MVAPIC. And we call that a transitive splice because we get the transitive dependencies through the newly spliced in package. And so in this example, here's the deployed spec, circled in black or purple. And that's what's on disk. And the rest of it may or may not be on disk, but at least we have the recording of how it was built. We could reproduce it if we need to debug something. We haven't lost information. There's also intransitive splices. So imagine you've deployed a really fast binary for MVAPIC, and you've made that available to other people, and they want to swap that into their builds and see if it gives them better performance. So you swap in MVAPIC prime, but you have to redeploy it now against the existing zlib in the package that you're installing with. Imagine, right, ABI compatibility is a one-directional model. So you might need to use the newer zlib from the application. So now we've got a Trilinos star, and it's deployed with MVAPIC prime star. That is the spliced MVAPIC prime that points back to the zlib that originally came with Trilinos. So that's an intransitive splice. You can see, okay, this is deployed on disk. The rest of it may or may not be. And in this model, what I've talked about so far, everything I've talked about has been shared dependencies of both. Because those are the only ones that are actually interesting. If it's not a shared dependency, you just take it from whichever one has the dependency. It's easy. Transitive and intransitive are all the same in that case. All right. So ABI constraints. This is where we start to get a little vaguer. You can tell I'm getting closer to the end of the talk because I'm going to switch into the future tense a bit. But we need some way of checking that these spliced specs will actually work. So here we've got a a different layout, but this is another transitive splice of Trilinos, the same setup we've talked about, but pointing out the ABI compatibilities that we have to check. We have to check that zlib prime is ABI compatible with zlib, or at least ABI compatible with the portions of zlib that Trilinos star cares about. And similarly for these other edges. So we're working on a model for ABI specs to allow packages to encode the information of which parts of their spec are ABI relevant. Some things are obvious. The architecture that you're built for is always going to be ABI relevant. But other things are much less obvious. You need some very detailed package-specific information to know whether the change in versions from 1.2.10 to 1.2.11 in zlib changes the ABI or not, right? What functions were modified? Are there function signatures changed? Are any types changed? Are those types exported to the caller? So we're gonna, and then for variants, for build options, those may or may not be ABI relevant depending on what the option does. If it adds symbols, well, okay, that's ABI relevant in one direction but not the other. If it removes symbols, okay, you flipped it. Some build options swap out symbols completely, and some build options don't change symbols at all, right? Position-independent code. You might have a build option for it. It's not going to change your ABI unless you're building statically. All of what I've talked about is package-level ABI. But we also want to model function-level ABI, because not everything in your ABI is necessarily exposed to your dependents, and even less maybe to their dependents. So we've got a model here of, package A depends on B, depends on C. They all use the C++ runtime, which maybe isn't part of the model. And that's how we're modeling compatibility. But we want to be able to model what types actually changed. If CE defines a type T3, and we've got these function calls with the type signatures in, we can see, looking at this model, that a change to T3 does not actually change the ABI of package A, and you could swap those in interchangeably without needing to rebuild. But we have this type T1 that comes from the C++ runtime, and if you get a different runtime, you need to rebuild all of them. Because they all depend on that type, you're not going to be able to get away with swapping it. So we want to run entry and exit calls, data types, all of the runtime libraries that come from the compiler, the GPU runtimes, and we want to model those changes through the graph so that we can properly determine programmatically, instead of by expert oracle, which splices we can make, when we can take your MVAPage2 binary and splice it into my application, and vice versa. So that's all I've got. Any questions?
Let's thank the speaker first. Do you have any questions? Any online questions, Nat? Okay, let's thank the speaker again. Thank you. Thank you. So our next talk is MUG'22 at NERC.